I'm going to talk about a story involving matroids, tropical geometry, and K-theory. But before I do that, I need to talk about an older story involving matroids, tropical geometry, and cohomology. This second story was worked out roughly between 1995 and 2015, so that's before I entered grad school, so I'm entitled to call it classical. The setting is you have some linear subspace of C to the n. Doesn't really matter that it's C. And yeah, so it's a linear subspace. And it has dimension R. And it's also important to assume that L intersect C star to the n, so it intersect with the torus, is not equal to, is non-empty. So i.e. that L is not contained in any coordinate hyperplane. Then this situation, it gives you a matroid M, which is loopless because of this not contained in a coordinate hyperplane assumption. Okay. So then PL intersect with C star to the n mod C star is a subvariety of the torus. So it's non-empty. So you can tropicalize it and get something interesting. And this tropicalization is the Bergman fan. So it's some object called the Bergman fan of M. So this tropicalization, it doesn't come with a canonical fan structure, but there is a fan structure. Yeah, it's just some subset of R to the n mod R times the all1 vector. But there is a fan structure on it that I particularly like. It corresponds to the maximal building set. Yeah, so you get some fan. It has dimension equal to the dimension of PL, so it has dimension R minus 1. And it's a smooth, non-complete fan. Okay. And you can consider the Chow ring of the Bergman fan, or of the toric variety corresponding to the Bergman fan. So this is a graded ring associated to this fan. I should say the rays are in bijection with proper non-empty flats of M. So this ring, it has one generator for each ray of the Bergman fan. So yeah, rho is a ray. So it has one generator for each proper non-empty flat. And then there are two types of relations. So it's not super important exactly what they look like, but or exactly what they are, but the general shape is that you have some monomial relations, which happen to be quadratic. So you have x rho 1 times x rho 2 is 0 if like the convex hull of rho 1, rho 2 is not a cone of your fan. So there are these monomial relations. And then there are also linear relations. So you have a linear relation for each pair ij in n. So the linear relations, they look like you sum over the rows, the rays. So rho is a ray of this is like a primitive vector on the row, on the ray, v rho. And then you take the ith coordinate and you multiply by x rho. And then that quantity is equal to the sum over the rays of the jth coordinate. Okay. Where, yeah, here I and j are some elements of 1 through n. Okay, so it's not too important, but there are some, this ring has like a simple presentation, and there are some monomial relations, and then there are some linear relations. Okay, so this ring, it has an additional structure, which is that there is a map called deg from the degree r minus 1 part to the integers. Non-zero map, distinguished map. And this corresponds to the fact that sigma m is a balanced fan. So giving a balancing on sigma m is more or less the same thing as giving such a map. And turns out because it's the tropicalization of a subvariety, it admits a balancing, and it turns out up to scaling, there's a unique balancing. And then, yeah, there's a distinguished such guy. So one thing you can do is that we have this PL intersect our torus, and I can take the closure of PL intersect the torus inside of this, the toric variety corresponding to this fan. So this is the toric variety corresponding to sigma m. Right, so this toric variety, it's like n-1 dimensional, and it's a non-compact toric variety, but it contains the torus by construction, and this is a subvariety of the torus, and so I can take the closure of this subvariety in there. And it turns out that you get something compact, and this is the wonderful compactification of PL intersect the torus. So this variety was constructed by DiConcini and Perchesi. It's smooth and compact, proper. So you have this toric variety, which is, it's like not such a nice thing from the perspective of algebraic geometry because it's not compact, but it contains this beautiful subvariety. And there's a nice relationship between this toric variety and its chow ring and this subvariety. So it's a result of Feichner and Uzinski from 2004 that there's a restriction map from the chow ring of sigma of this toric variety, so the chow ring of sigma m, to the chow ring of WL, which is this wonderful compactification is like a very nice variety, and so its chow ring is isomorphic to its cohomology ring. And this restriction map is an isomorphism. Yeah. Sorry. So WL is the wonderful compactification. And yeah, so right. So if you take this nice compact subvariety sitting inside there on the level of cohomology, yeah, so the cohomology, this compact subvariety is the same as the cohomology of this non-compact guy. So that means that this chow ring of a matroid, yeah, so this is sometimes called the chow ring of a matroid. So it's the chow ring of some non-compact variety, but in fact, when the matroid is realizable, it coincides with the cohomology ring of a smooth projective variety, and the cohomology rings of smooth projective varieties have like amazing positivity properties. And so it's natural to ask, like, for just a random matroid, which is not necessarily realizable, does the chow ring has some combinatorial presentation? Does it have the same positivity properties? And this was proved by Adiprasito, He, and Katz. So what they showed is that for any matroid, maybe any loopless matroid, the Chow ring resembles the cohomology ring of a smooth projective variety. Smooth, let's say, complex projective variety. So yeah, so more precisely what they showed is that it satisfies a version of Poincare duality so this is like saying that first of all, this Chow ring of matroid, it resembles the cohomology ring of a manifold. The cohomology rings of manifold satisfy Poincare duality. And it also satisfies the Hard-Lefschetz, the conclusion of the Hard-Lefschetz theorem, and the Hodge-Riemann relations. So it carries a polarized Hodge structure. Okay. So a couple comments about this. One is that, so I said that there's a degree map, and then if you, basically that's all you need to do to formulate the statement of Poincare duality, but the statement of these two, they refer to, like in algebraic geometry, they refer to ample elements. So this is some statement that for every ample divisor or something happens. And so you need to, in order to just even say what this means, you need to like be able to talk about what is like an ample element of that. So okay, they do that. There are kind of multiple reasonable definitions, and yeah, and they choose one and show that it works. The second comment maybe is that this is like really kind of a special statement about matroids. So if you just choose like a random tropical fan, this is very unlikely to be true. And there's not really like some general result that contains this. So there are now somewhat simpler proofs, but all of the proofs really use some very like explicit properties of this fan. So if you take a Bergman fan of a matroid, so something which satisfies the conclusion of this theorem, and you apply some random change of coordinates, and then hand it to some expert on, combinatorial Hodge theory or whatever, and ask them to check, like ask them whether it satisfies this without telling you how you got the fan, they're not going to be able to. So there's no simple criterion you can check to see if this satisfies. You really need to like know where your fan comes from. Okay, any questions about this classical story? So it is determined by the support. So there are theorems that like if you take any smooth fan structure on the same support, then whether these properties hold, yeah, it only depends on the support. But if somebody just like hands you a fan, tells you a list of 1,000 rays and then what the cones are, then there is like no reasonable thing you could check to see if these hold. Like, yeah, basically the only way people know how to prove this type of things is through some inductive procedure. And if somebody hands you a fan and they tell you, oh, it arises from this inductive procedure, then maybe you could check whether it holds. But if somebody just hands you the fan as like a list of rays and cones, then there's no reasonable way to check whether this is true. Yeah, I mean, maybe in an example, it's like kind of finite computation, but if you give someone like a family of examples, All right, so I'm going to talk about, so this is like essentially a cohomological story, right? There's like the cohomology here. I'm going to talk about a version for K-theory. So let me say what that means. So if I just have some smooth variety with complex numbers, say, then there's a ring K of x, which is the Grothendieck ring of vector bundles. On X. Okay. So what that means is that it has a generator for each vector bundle on X, and there's a relation for each short exact sequence of vector bundles. So you kind of you split the short exact sequence. So if you have, 0 goes to F1, goes to F2, goes to F3, then you set the class of F2 is equal to the class of F1 plus the class of F3. This is a ring because when you tensor with a vector bundle, if you have an exact sequence and you tensor with a vector bundle, then it stays exact. And so there's some product given by tensor product. And it has a map to the Grothendieck group of coherent sheaves, which is an isomorphism because X is smooth. Okay, so this is some ring you could define. And it has some additional structures. So just like the cohomology ring of a variety has a grading and a degree map, and this also has some additional structures. So it's a filtered ring. So it's equipped with a decreasing filtration, and the associated graded of this ring is the Chow ring of your variety, which is some version of cohomology. And it also has the structure of something called a lambda ring. So what that means is that, if you have like a vector bundle, then you can take its exterior powers. So this is like some operation you could do to vector bundles. And it turns out that the class in K-theory, if somebody hands you a vector bundle, then the class in K-theory of the exterior power is determined by the class in K-theory of the original guy. And so there's this operation where somebody hands you a class, and then you take its, like, what would be the exterior power if it's the class of a vector bundle. So this is like well-defined, and it satisfies some complicated relations and whatever. It's not that important, but there's just various additional structures that you have for free because something is the K ring of a variety. Okay. Yes. So algebraic, algebraic vector bundles. So if X is compact, proper, then there's a map chi from the K ring to Z. So this is given by the sheaf Euler characteristic. So if you have a compact variety, then you can talk about the sheaf cohomology of any coherent sheaf. So the vector bundle is a coherent sheaf. And then you can sum the dimensions of those up with alternating signs, and you get some number. And this only depends on the class in K-theory. So the existence of such a map really requires X to be compact. And if X is nice, then the map, the pairing AB, where you take two K classes, and then you map them to the Euler characteristic of the product, is a perfect pairing. So meaning like it's non-degenerate after you tensor with Q, let's say. So nice means something like the algebraic K-theory coincides with the topological K-theory. So this is like some sort of K-theoric analog of point graded value. Okay. Yeah. Okay, so for any smooth variety, you can consider this ring. And so there's a smooth variety over here. So this torque variety of the Bergman fan. So the fact that the fan is smooth means that this variety is smooth. And you can, consider the K theory of the Bergman fan. And Vistali and Viscosi, they computed a presentation of the K ring of any toric variety, smooth toric variety, possibly non-compact. So what they showed is that the K theory of this Bergman fan has a presentation that looks like this. So as before, as with the Chow ring, you have one generator for each ray. So this generator is going to correspond to the structure sheaf of the corresponding divisor. And then there are, again, two types of relations. So there's the monomial relations, which are exactly the same. So this is y rho 1 times y rho 2 is 0 if rho 1 and rho 2 don't form a cone. So not a cone. And then instead of this linear relation before, there's like some more complicated relation. So what it looks like is you take the product over all rays of 1 minus y rho to the the ith coordinate of the primitive vector. And then you set that equal to the product over all rays of the jth coordinate of the primitive vector. And you do this for all I and j in 1 through n. So this relation, if you expand it out, then, okay, so if you look at the term that involves like ones, that term cancels between these two sides. You have like a 1 here and a 1 here. And then the next term, if you look at the term involving that's like linear in the row i's, then that is exactly this relation. So this relation, it's like some complicated nonlinear thing. And if you just look at the lowest order term, then you recover the original relation. And that's like the reason why this happens is because this this ring is filtered, and the associated graded is that ring. So you just you in the Chow ring somehow you throw away like the lower order data, and here you're keeping it. Okay. So so before we have this inclusion of WL into the toric variety of the Bergman fan, and there was a restriction map on Chow, which was an isomorphism, and the same thing happens here for a simple reason. So there's a restriction map. This K ring is like a contravariant functor. So whenever you have an inclusion, say, there's a restriction map so there's a restriction map from this ring to the K ring of the wonderful compactification, which is a smooth projective variety. It's compact. And this is an isomorphism. And this is true for a simple reason, which is that this map between the two K rings is a filtered map. So both of these rings are equipped with filtrations. And the associated graded of this map is the map between Chow rings, which Feichner-Niedzwiński told us was an isomorphism. And it's just like some general fact about algebra that if you have a map between like filtered abelian groups and the associated graded is an isomorphism, then the filtered map is already an isomorphism. Yeah, so there's no torsion. Yeah. So this is it's non-obvious fact that there is no torsion in the Chow ring of a matroid, and that implies like if you have a a filtered abelian group, finite dimensional, say, or finally generated, and the associated graded has no torsion, then it already has no torsion. Yeah, so what this means is that if M is realizable, then this K ring of this Bergman fan is the K ring of a smooth projective variety. In particular, that means that it admits a sheaf, like an Euler characteristic map like this. And it turns out this wonderful compactification is like wonderful, and in particular, it's nice. And so this this pairing is non-degenerate. Okay. So are there any questions? Yes, yeah. So it's an isomorphism of lambda ring. Yeah. So like I mean, this is not really a rigorous proof, but this map is, this is where the lambda ring structure comes from, and then taking like exterior powers of vector bundle commutes with pullback, and so yeah. Okay. Right, but it's unclear whether this persists for like all matroids, right? Because it's like not that clear even how to define the Euler characteristic map. If you just like from this presentation, presentation is kind of complicated. But there's so there's something you can do, which is that, right? So the wonderful compactification, it's a compactification of PL intersect the torus. And in fact, the boundary, one of the things that makes it wonderful is that the boundary is a simple normal crossings divisor. And the boundary, the irreducible components of the boundary are indexed by rays of the Bergman fan, so by proper non-empty flats. So for each proper non-empty flat, you have a divisor on the wonderful variety. And in fact, each of these divisors is a product of smaller wonderful varieties. So there's a short exact sequence for each of these divisors. 0 goes to O minus D rho, goes to O structure sheaf of D rho. So this is on the wonderful variety. We have a short exact sequence like this. And if we tensor this with some line bundle of the form OWL of some A rho D rho, D tau. So you take some line bundle, which is O of a bunch of these, the line bundle corresponding to this divisor, where you sum up each of these guys with whatever coefficients you want, then we get a short exact sequence like this. You get 0 goes to O of, now you have like A rho minus 1 D rho plus some tau not equal to rho, A tau D tau, goes to O of some A tau D tau, goes to O D rho, you restrict it. Yeah, you restrict this line bundle. Okay, so I just took this short exact sequence and I tensored with this guy. And another thing that we know is that the Euler characteristic of the structure sheaf of WL is 1. Because WL is, it's smooth and smooth projective, and it's a compactification of projective space. And if you look at the higher cohomology of, not a compactification of projective space, it's birational to projective space. And if you look at the higher cohomology of any rational variety, higher cohomology of the structure sheaf of any rational variety, then there's like it's one-dimensional in degree 0, and all the higher stuff is 0. So that tells you that this is 1. Okay, so what you could do is, if we imagine that, say, maybe all these a tau are positive, and we're trying to compute what the Euler characteristic of this is by induction. So this defining relation in the K-ring tells me that the Euler characteristic of this plus the Euler characteristic of this is equal to the Euler characteristic of this. And here, this D rho, okay, it's not quite a smaller wonderful variety, but it's a product of smaller wonderful varieties. So I'm going to imagine that I know what to do here. So I know by induction. And then this term, it's like closer to being like chi of O. So maybe I also know what to do here by induction. Then that determines what the Euler characteristic of this is. Right? So maybe I'm inducting on like the sum of the absolute values of the A row or something. So this relation, it determines what the Euler characteristic is. So as long as you know chi of the structure sheaf is 1, and you know like what happens for lower dimensional stuff, then using this relation in enough pain, you can compute the Euler characteristic of any line bundle of this form, but in fact, every line bundle is of this form.
Wouldn't you need to know what the normal bundle looks like?
Yeah, so you need to know how to restrict here, if that's what you're asking. Which you know. So that is a computation. Yeah, so that's like a cohomological computation. You just need to know what C1 of the normal bundle is. And that's like determined on the level of Chow, and then yeah, you can work out what happens. So right, so this determines chi. But there's like a lot of redundancy here somehow. So there are these linear relations in the Chow rings, in the Chow ring, which corresponds to the fact that, okay, every line bundle can be expressed in this way, but in multiple ways. And so it's not obvious that this is like a well-defined procedure. So I just gave you an algorithm to compute the Euler characteristic of any line bundle, but it's like not obvious that there's some choice involved in how you express your line bundle in this form, and also some choice in like, you're decreasing the coefficients, but you could decrease them in various orders. But it's not like obvious that the answer is independent of the choices. So in the case where you have the wonderful variety, so this algorithm, it makes sense for any matroid. I mean, it depends on like some large number of choices, but you can make such choices for any matroid and run this algorithm. And in the case of the wonderful variety, this is actually computing like some algebro-geometric quantity. And so you know that like the answer doesn't depend on the choices. But for arbitrary matroid, it's like not really not obvious that the answer is independent of the choices, because the relations in the K-ring are like complicated. Okay. So then our result with Shirya Lee, Sam Payne, and Nick Proudfoot is that basically it is defined. So there is a map chi from the K-ring of this Bergman fan to the integers. So from the ring with this presentation to the integers, which you can compute using this algorithm. And it also satisfies this thing that holds for like nice, smooth projective varieties. So, and yeah, the pairing AB maps to chi of AB is perfect. So yeah, if you represent it in some, this is like a finite rank torsion-free abelian group, and if you represent it in some matrix, then that matrix is going to be unimodular. Yeah, so any questions about the statement? Okay, so one thing I should say is that this procedure that I outlined for trying to compute the Euler characteristic, if you think about it enough, then it makes sense for any fan. So you can do something like this for any, come up with this procedure for any fan. Maybe it's not clear that like this is the right choice there, but and there's a forthcoming paper by Melody Chan, Emily Clater, Carly Clivens, and Dusty Ross, where they consider like this procedure and they analyze when does it give you something well-defined. And the answer is, sometimes it does, sometimes it doesn't. So one thing that's not hard to check is that if this procedure gives you something well-defined, then that implies that the your underlying fan is balanced and all the weights are 0 or 1. But that's also not a sufficient condition. But I think that like even after the work, this is like a non-trivial computation. So we have to like really do something kind of matroidy, like do some somewhat serious work in order to prove that this is even well defined, and then the perfect pairing is something else. And I think that this type of statement is just like more difficult than showing that the Bergman fan is balanced, for example, which you can do fairly quickly. So now I'm going to talk about two applications. So the first application is relating two types of computations that people have done in the literature. So there's a group of people who've constructed various algebras associated to hyperplane arrangements. So I'm thinking of this L contained in CDN as like you have the coordinate hyperplanes, and that gives you a arrangement of hyperplanes in L. So let me just write down some names of algebras that people have studied. So maybe the most classical is this thing called the Orlik-Solomon algebra, which is the cohomology ring of L take away the union of the hyperplanes. This is like some very well-studied object. And then there's there are a bunch more that I'm not going to define. There's the Orlik-Tarrau algebra, which is some sort of commutative deformation of the Orlik-Solomon algebra. There are these things called zonotopal algebras, which were studied by Ardila and Postnikov. And then, very recently, there's a sort of non-commutative deformation of the zonotopal algebras, which was considered by Brendan Rhodes, Vasu Tewari, and Andy Wilson last year. And people study like various aspects of these algebras. But one thing that people like to do is you compute, these are all graded algebras, and you can compute the Hilbert function. And it turns out that in these examples, you always get some sort of known matroid invariant. So usually you get something related to the top polynomial matroid. So for the Orlik-Solomon algebra, the Hilbert series is the characteristic polynomial of your matroid, okay, with the coefficients written backwards, which is some like very well studied, very well studied matroid invariant. So there's another thing that people have done in the last 10 years, which is 10 or 15 years, which is that you can do intersection theory in the Chow ring of the Bergman fan of a matroid. So it turns out that, so there are all these log concavity conjectures that various matroid invariants are log concave. And it turns out that the key to proving one of these conjectures is, well, at least the first step is to realize whatever matroid invariant you're trying to study as an intersection number in the Chow ring of a matroid. So what this means concretely is that you have this, you have this ring, and then you want to find like a bunch of elements such that when you multiply them together, you land in so that you land in degree r minus 1, and then take the degree map, so you get a number, then that gives you your original matroid invariant. Okay, so there are more things you need to do in order to prove the log concavity conjecture, but that's like step number 1. Okay, so people have, motivated by the desire to prove these conjectures, people have studied this a lot. So the first result of this form was by Jun He and Eric Katz from 2012. There's also a result by Alufi from shortly thereafter. And then most recently, there's a result by Chris, Jun, and myself from a couple years ago. Okay. And then, yeah, there are many more. These are just 3 that I'm saying for some reason. So it turns out that these algebras, in each of these cases, maybe conjecturally in the last case, you can realize them as the sections of some vector bundle on the wonderful variety. So the Euler characteristic of a vector bundle, it's not quite the dimension of the sections, but it's like kind of close. And it turns out that in at least these 3 cases, the higher cohomology vanishes for the relevant vector bundle. And so you could compute the Hilbert function of this algebra as an Euler characteristic computation. On the, in the K ring of the wonderful variety, which is equal to the K ring of this Bergman fan. And right here, this is some question in the Chow ring of a matroid. And it turns out that there's, we construct some special relationship between the K ring of a wonderful variety and the Chow ring of a matroid. So between the K ring of the matroid and the Chow ring of the matroid. And we call this the exceptional Herzberg-Riemann-Roch theorem. So Herzberg-Riemann-Roch is some statement saying that if you have on any like smooth projective variety, you can relate Euler characteristics to intersection numbers. Turns out that that is not that useful here because the Todd class is like very complicated. But there's some substitute that you can do that relates Euler characteristic computations here to intersection theory computations here. And when you plug these Euler characteristic computations into that machine, then you get exactly these intersection theory computations. So it turns out this formula that the Hilbert function of the Orlik-Solomon algebra is the characteristic polynomial. It relates to this computation of Alufi, which relates the Chern-Schwarz-McPherson classes of the wonderful compactification to the characteristic polynomial. This Orlik-Trow algebra is related to this He-Katz computation, and then both of these are related to this result. So it's not, So in some sense, this shows that people were really studying like the same object. Although it's not, I'm not claiming that you can, if you understand this side really well, you can prove all these results or the other way around, because actually showing that like all the higher cohomology vanishes, and so the Euler characteristic of this thing is what you expect it to be, is like not always that easy. But at least after the fact, in these 3 cases, you can, you can prove, given these 3 things, you can prove these 3 things. Special case of this. Okay, so are there any questions about that? Ah, okay, good. Nervous. So the other application that I want to mention is, yeah, I was kind of trying to sell our result as saying that, well, there's this famous Adiprecito-Ho-Katz theorem that shows that the Chow ring of this non-compact variety behaves like the Chow ring of a smooth complex projective variety. And you know, we're doing the same thing in K-theory, but you could complain that the hard part of this Adiprecito-Ho-Katz result is really the Hard-Lefschetz theorem and the Hodge-Riemann relations, which are really statements about like ample divisors and stuff. That this is really, it's really telling you that the K-ring of this Bergman fan behaves like the topological K-ring of a manifold. So it's like sort of a topological statement rather than a statement about, you know, complex projective varieties, it's the analog of some topological statement. But there is we do have a conjectural statement that is more similar to this Adiprecito-Ho-Katz thing, where it's saying that there are positivity properties which are satisfied by K-rings of smooth complex projective varieties, and we think that those properties should also hold for the Bergman tan. And that positivity property is related to Kodaira vanishing. So if L is an ample line bundle on X, some smooth complex projective variety, then Kodaira vanishing says that HI, so the sheaf cohomology of X with coefficients in L, the inverse of L, is equal to 0 for I less than the dimension of X. Each I. So what this implies is that if I take the Euler characteristic of L inverse, then this is equal to the dimension of H0 of X L inverse minus plus minus 1 to the dim X times the Euler characteristic times H dim X of X L inverse. And all of these terms are 0 by Kodaira vanishing. So the only surviving term is this guy. So that tells you that like what the sign is of the Euler characteristic of L inverse. So it tells you that minus 1 to the dim X times the Euler characteristic of X L inverse is greater than or equal to 0. And I should say that this really requires the complex number. So it fails, even this statement fails if X is in positive characteristic. So then natural question is, does this hold for matroids? Yeah, and there are sort of stronger things you could ask for. So there's a strengthening of Kodaira vanishing called convolutive Vivek vanishing, which only requires L to be nef and big rather than ample, and you get the same conclusion. Okay, so if you want to ask whether this holds for ample. Yeah, if you want to ask whether this holds for matroids, then a question you need to answer in order to formulate this is, what does ample mean in the context of matroids? Right, because this is some statement about ample line bundles. And yeah, there are sort of various definitions that you could put forth, but one is that it turns out that this toric variety of the Bergman fan is contained inside some particularly nice smooth projective toric variety. called the toric variety of the permutahedron. And if you take some ample line bundle on here, then that defines a class in the K-ring of this guy, and then you can, maybe that's a reasonable definition of ample. And there's a conjecture by David Spire, which it says that like for a special L, Euler characteristic of L inverse times -1 to the r minus 1. So the dimension, the analog of the dimension of X is the number r minus 1. So the dimension of PL is greater than or equal to 0. And he has some application to this for this statement. So this is from almost 20 years ago. So Spire was interested in bounding the number of faces a tropical linear space can have. And he does a lot of things, and then he reduces it to showing that this is true for some specific L which he constructs on the wonderful variety. At least that's one interpretation of what he does. And so in his paper, he says, well, by Kodaira vanishing, it's true if your matroid is realizable in characteristic 0, and then he conjectures that it's always true. So unfortunately, I don't know how to prove a general statement like this, but Chris and myself, we have proven this is true in some cases. So what we can show is that if L satisfies some stronger notion of ampleness, so if L, I'm going to call it simplically positive, then the Euler characteristic of L inverse times -1 to the r minus 1 is greater than or equal to 0. And this implies Spire's conjecture in new cases. So whatever this L that Spire considers, it's not always simplicity positive, but you can write down like a formula for exactly when it is simplicity positive. Or it's like simplicity positive if some random looking sum happens to be positive. And then you can check that there is at least one example of a non-realizable matroid where it is simplicity positive. In fact, there are infinitely many. But yeah, it's not always true. Okay, so yeah, let me just say very briefly the geometry of why we're able to prove this. So there is an embedding of the wonderful variety into a product of projective spaces. Okay, so I'm not going to say where it comes from, but there is some specific embedding like this that I'm thinking of. And this, if you think of it as a homogeneous space. So projective space is like GLN modulo a certain parabolic subgroup. And so a product of projective spaces is like a product of GLNs modulo parabolic subgroup. And so there's a Borel acts on the product of projective spaces. And you can use that to degenerate WL to some Borel fixed subscheme, which happens to be reduced. So this is like taking the generic initial ideal in some sense. And the Euler characteristic of L, of F on WL, so I'll call this ym. Turns out it only depends on the matroid, is equal to the Euler characteristic on ym of F. So if, for example, okay, this, as I wrote it, maybe doesn't strictly make sense, but if you have some line bundle which is up here and you restrict it to WL or you restrict it to this ym, you get the same thing. And turns out the restriction map on pick is surjective here. So if you have any line bundle on WL, you can lift it to here and then restrict it to YM, and you can compute the Euler characteristic of anything you want on YM. And yeah, so YM is defined for any matroid. And in fact, this formula, it works for any matroid. So if I have any line bundle on the Bergman toric variety Bergman fan, I can choose a lift to this product of projective spaces. So that means something like concrete. And then restrict it to this YM variety. That's now a, okay, it's not, it's reducible, but it's like an honest scheme. And I can compute the sheaf Euler characteristic on that scheme, and I get a number, and that number is the Euler characteristic that we construct over there. And YM has the further property that it is Frobenius split. So yeah, so you can, the equations defining YM are defined over Z, and you can reduce modulo P, and then it has some, for your favorite prime P, and then it has some special property, this reduction of YM mod P. And this Frobenius splitness implies a version of Kodaira vanishing. So even though Kodaira vanishing fails in positive characteristic, it holds for Frobenius split varieties. And so we can compute our Euler characteristic on this Frobenius split variety, and then we can make use of Kodaira vanishing. But the problem is we need to know that it's an ample divisor on YM in order to apply Kodaira vanishing. And if you start with an ample divisor here, it might no longer be ample here. But this simplicity positive condition exactly means that it's ample on this product of projective spaces. And so when you restrict it to YM, it stays ample. Yeah. Okay, I'll end there.